Hello, in this lecture I will talk about my research work and we can also discuss some research direction. So basically during my PhD and currently what I am doing is like there are multiple topics that I'm working on. So I will go through those topics one by one. So the first topic is related to the interpretation of deep neural network. So actually what is interpretation? Like we want to know how this neural network works. We want to interpret what is learned inside the neural network, because the neural network is a multi-layer network and we don't know what is inside those layers, because there are nonlinear activation functions and architecture is also multi-layer. And what we are doing normally is we give the input, we get the output, and then train the neural network end to end. So we are unaware of the what is going on inside this neural network. So we in one part of this lecture I will try to unveil this to show how can we interpret this neural network. The second part of this lecture will be based on enhancing the grasping accuracy of the robot. Like suppose this is one example. So the robot take a picture of an object. So if it does have the information of that object, like if it contains the full information, the model of that object, then it can grasp it accurately, because it can open its arm based on the available information. So uh, here in this part I will discuss about how we can improve the grasping accuracy of the robot. So this is actually related to the 2D to 3D transformation. Like the robot take the image or the picture of an object, and we take that 2D image and we transform that 2D image to 3D representation. Once we have the 3D model of that object, then the robot has better understanding capability, like it has the size or volume of that object so that it can open its arm and grab that object. The third one is related to image translation. So it has many different applications. So suppose this is one simple neural network. This is a classifier where we train this classifier on input images. Suppose these are the cat images. We are providing it to this neural network, and at the output we provide its corresponding label. Like suppose this neural network should generate the label for this input image, which is cat. But actually when we train this neural network, the testing samples may be different kinds. Like suppose this is also one kind of input image. Here we can see that this is a cat, but it is mostly occluded. uh, Similarly, uh, there may be some missing parts in the input image, which can also affect the accuracy of this neural network. The third one is noisy. Like if the input image is noisy, then it can also affect the accuracy of the neural network. In the second part of this image to image translation topic, I will also discuss about how can we estimate the depth map uh, from the given RGB image, from the given single RGB image. So this is a related to, like suppose this robot is moving. So if it does have the information of the terrain, so it is used in terrain analysis basically. If this robot is moving and if it have the information of the terrain ahead, then it can decide which way to go, and it can also avoid the tip over. Like suppose if the robot go this way, so this is not a possible path. If it go this way, it can tip over easily. So it has to find its best possible path. The Third one is related to the content modification. Like suppose this is the face image. So what we are going to do is we want to modify the contents or some features in this face image. So suppose this is a person with eyeglasses, so we want to remove the eyeglasses from him. Similarly, we want to change the hairstyle, or we want to convert him to some other gender. Similarly, you can see here. So this is related to the content modification. Like we can change the different contents in the face image, and it also has many important applications like suspect identification. Like if there is a suspect, we can change his different attributes in the face and then analyze which one suits and which can give us the proper results. So it has many different applications. I will go through this in detail when I'm discussing the related topic. Now I will come to the first part of this lecture, which is related to the interpretation of deep neural network. So the topics of this part includes motivation, then the related work to this interpretation of neural network. I will also discuss the feature extraction and reconstruction network that we developed for this particular task. And then I will also discuss the response field-based reconstruction algorithm, why this algorithm is important, and we will use this feature extraction and reconstruction network to analyze the wrong and correct classification using the clustering based approach. And we will also perform the feature interpolation by using this approach. And also we will investigate the neuron learning capabilities toward a structured representation of the data. There are some videos I will show like how it can perform classification and also interpolation. So what is the motivation behind this work actually? So interpretation is actually very important. We want to know how this neural network learns. So one way to interpret neural network is like once we train the neural network, what we do, we provide the input image and then we classify it. If it do accurate classification, if the classification is correct, we can say that this neural network learned the data properly. So this is just one rough way of understanding the neural network, but there are many meaningful ways to interpret neural network, what is inside those neural network. Like this classification only shows the end-to-end interpretation. It does not show the interpretation of neural network between different layers. So another way is visualization, like how we want to visualize those neurons, like what those neurons are learning. And secondly, we also want to find the collaboration, how those neurons collaborate with each other to give the final results. Similarly, we also want it, if the neurons are collaborating with each other, then it must have some interpolation capabilities, and this interpolation find how features are combined. Like interpolation is only possible if the features show some relation with each other. So based on these motivation, I follow this interpretation of neural network by using the feature extraction and reconstruction network that I will explain in the coming slides. So now let's talk about the related work. The first approach that is based on visualizing what is learned inside neural network is the gradient based iterative optimization. So how it works, like first they trained the neural network, the classification neural network. After training the classification neural network, what they did, they provide the input image which is not image but a random noise, and then they pass this random noise through the network and get the recognition probabilities. So suppose if a neural network is trained on 10 classes, so the first class label should be 1 0 0 0 0 0 to 10, and the second class label will be 0 1 0 0 0, the third class label will be 0 0 1 0 0 0 0, something like that. So what they did, they pass this noise image as input to the neural network, and then they wanted to know what is learned for the first class. So they fix the label is, suppose for the first class they fix this label 1 1 0 0 0 0. So this is the label for the first class. They fix this label at the output, and then they provide this noise image as input to the neural network. When they provide this noise as input to the neural network will generate some label, and the weights are fixed. The weights, once the training is done, the next step is the interpretation. So the weights are fixed. Using the fixed weight, we give this noise as input and generate the label, but we don't know because this label is based on the random noise, so it is meaningless. So what they did, they want to maximize this recognition probability for the first class based on this input noise image. So first they give this noise as input, generate a label, and then they use the back propagation algorithm. The weights are fixed, but they change the value of this input image based on the cost function which is provided here. So they generate the label, and then they try to maximize that label to get class 1 label out of this noise image, and the variable here is the noise. So they are changing the noise in iteration, and after few iteration they got the image which is kind of mixture of different objects in the class 1, suppose. So here we can see that there are many shapes, this one, like this is this way. So these are the different variations of the samples belonging to class 1 based on this iterative optimization approach. The second one people do is they train the neural network, feed forward neural network, and after training they attach decoder to each and every layer to get what is the output from the first layer, what is the output from the second layer, and what is the output from the third layer. So here these are the results from the, I think these are the results. I took this picture from the corresponding paper. So these are the results from the third or fifth layer, and this is the result from the second last layer, I guess. So here we can see that as we go up towards the classification part of the network, the result is more kind of mixture. Oh sorry, so this is like, this is the first layer, this is the second layer. So in between, this is the activation layer, this is the pooling layer, and this is the normalization layer. Similarly, this is the second layer, this is the third layer output, this is the fourth layer, this is the fifth layer output, this is the sixth layer, fully connected layer. The previous one was the convolution layer. So here we can see that the convolution layer output is somewhat more similar to the input image, but as we go to the fully connected layer, it has become mixture of many objects. So this is the sixth layer, seventh layer, and the eighth layer. So here we can see that the eighth layer is the mixture of different objects. So this is how they analyze or interpret the neural network. The other approach, they use the normalized contribution approach. So what they did, they provide the input image, and then they pass it to the second last layer, and then they multiply the label of that image with the feature that is obtained from the input image, and then they back propagate those contributions to the input, and then they generate the heat map and analyze the neural network in this way. And this is called layer-wise relevance propagation approach. In our proposed approach, what we did, we first trained a feed-forward neural network, a classification neural network as a first step. After training the feed-forward neural network, we attached a decoder to this feed-forward neural network, and then train this feedback neural network or the decoder network. Once the training is done, we cluster all the features in the feed-forward path and the feedback path. And after clustering, we pass the test samples, and that test sample will collect its representative clusters in both directions. It will pick its representative cluster in the feed-forward direction, and it will pick its representative cluster in the feedback direction. And we will check if the selected clusters in both directions are same. If this testing sample is collecting the samples in both directions, then it means that this classification is correct, like this network is classifying the object accurately. If they are different, then there is then this is wrong classification. We will see this in the later slides. Here in this network, the reconstruction is possible from each layer and each neuron. So our architecture is very flexible. We can reconstruct from each layer and from each neuron. Like the previous approach, as I mentioned, they connect decoder to each and every layer, and there they were not able to reconstruct from single neuron. But here in this architecture, we can reconstruct from each layer as well as each neuron. Similarly, we also performed feature interpolation to see how these neurons collaborate with each other. And we follow a specific training strategy that remove that multiple decoders architecture, and to analyze whether this network learn the structure of the data or not, we put noise in the input samples and then reconstruct and check its ability, that how it behaves towards the noisy input. So I will go through these steps one by one in the coming slides. So this is the whole network that we proposed in our paper. So this is the feed-forward neural network. We provide the input testing sample. So by the way, this is 3D classification neural network. This is not 2D classification neural network. Like the input is 3D objects rather than 2D images. So it can be 2D as well, but here we use 3D neural network. So first we provide input 3D object to this classification network, and we get the recognition probabilities at the output. Here we use ModelNet 10 and ModelNet 40 dataset. The ModelNet 10 is the 3D dataset which consists of 10 different classes, whereas the ModelNet 40 consists of 40 different classes. So here we use ModelNet 10 and ModelNet 40. In terms of the ModelNet 10, this output should be 10 because there are 10 classes. So we train this deep neural network, the classification neural network, and once we train this, we attach this decoder part to this feed-forward neural network. So here we can see that this decoder is just one decoder, but it is taking input from each of its corresponding layer. So it decode this image back, the input image back to its input representation by using this decoder structure. So there are 3 different steps of learning this architecture. The first one is the learning the classification neural network, which is the first one, this one. The second part is learning layer wise. So first we learn this layer, then this layer, then this layer. So this is the objective for using the layer wise learning of this neural network. The third step is learning the whole decoder, like this whole decoder part. We give the input, sorry, this is the whole decoder part. So we give the input here and we generate this input take here. So this is end-to-end training. The last one is end-to-end training, the middle one is layer-wise training, and the first one is the encoder part training, or the classifier part training. Now I will talk about the response field-based reconstruction algorithm, like why we use this response field-based reconstruction algorithm. So basically, the convolutional neural network, we can see that the convolution operation is using a sliding window on the input image. So if I want to reconstruct, if I want to find the response field of this neuron, which is in the next layer, and this is the input layer, so the response field is this one. So logically, this is the response, this is the receptive field, and this response field should generate this whole receptive field, but that is not the case. When we checked in when we were doing this work, the single neuron output was meaningless. It was just kind of few points and it didn't have any meaning. So when we investigated this issue, we found out that basically the convolution operation is a kind of sliding window. So there are multiple response field neuron which are contributing to this this space. So what we did, in this algorithm we found the response field neuron for this input space, and then based on this input space we found the corresponding neurons in its neighborhood, where this region is common in all the response field neurons. So we found all those neurons for which this region is common. So we selected those neurons and use the collection of those neurons for which this region is common, this receptive field is common. So we reconstructed this input region by using those neighborhood neurons. So what I mean to say is, single neuron shows nothing. There are multiple neurons which work together, and those group of neuron is responsible for a specific receptive field, and this response field based reconstruction algorithm can effectively find those response field neurons that are responsible for a specific receptive field. Once we train this neural network, we cluster the feed forward and feedback features in both paths, and then we analyze this neural network in terms of the classification. So here this is the graph of the clusters that are selected by the testing sample. So here we can see that when we provided the testing samples in the feed forward path, this testing sample is saying that I'm belonging to the first class. This is 0 class, 1 class, 2 class, 3, 4, 5. There are actually we are using I was using the ModelNet 10 here. So there are 10 labels here. So the testing samples was belonging to first class in the feed forward path, and when we generate the recognition probability using the feed forward neural network, and when we fit those recognition probability to the neural network and then found the representative clusters to those recognition probability, it was again saying that it belongs to class 1. So here we can see that the clusters, the representative clusters in feed forward and feedback path are exactly the same. So it means that the classification is correct. So here this is the visualization by reconstructing those objects. So suppose input is a bed, and when we reconstruct this from this input, it give us the this bed peg. Like actually we can reconstruct from the initial layer as well as from the recognition probability. So and when we reconstruct the sample from the recognition probability, it is also saying the bed. So it means that the input sample is same as the one which is reconstructed from the recognition probabilities. Similarly, now this was the example of the correct classification. Now in terms of the wrong classification, so when I provided a testing samples, it selected class 1 as its representative clusters. But when I generated the recognition probability using this network, and I fed those recognition probability to this neural network in the feedback path, it picked cluster of class 2 as its representative cluster. So here in the feed forward path, the representative cluster was class 1, but in the feedback path the representative cluster is from class 2. So both the representative clusters are different in the feed forward and the feedback path. It means that there is misclassification. So here we can see that when we provide the input, suppose here is a bathtub, when we generated it from the local layer, so the local layer actually learned the input object, but when we go to the higher layer or upper layers, it learned the class representation. So when we generated this object from the local layer, it gave us the bathtub, but when we go to the recognition probability, it generated the bed here. So here we can see that the bed is different from the class of the bed is different from the bathtub, but it is classified as the bathtub. So here there is a reason. Actually the bathtub and the bed shape is similar. That's why the neural network found it difficult to differentiate these two objects from each other. Similarly, this is another example of bottle and the tree. So both shapes are similar. That's why the neural network found it difficult to differentiate between those two objects. But this clustering based approach provides us the way that if the selected cluster in both directions are same, it means that the classification is correct. But if they are different, then there is a misclassification. And how this how there is a misclassification, we can use this neural network to reconstruct what object like how it made the this error. So this is the way of reconstructing the input object back from its from the input as well as from the recognition probabilities. So we also performed the feature interpolation. So we interpolated the feature space by providing the input. Suppose this is the input bit, and then we changed the this feature space slowly to generate so that the bed is transformed to the gaming chair, and from the gaming chair it is transformed back to the easy chair, and from the easy chair it is transformed back to the bed. So we actually changed the feature space between these three objects and then see how it transformed from one object to another object. Actually we selected three different clusters, and we move from one cluster to another cluster by varying the feature with some alpha values, and then see how it transform from one object to another object. So this is the way of interpolation by using this approach. Similarly, this is another example of feature interpolation. Like this is a bed which is transformed to the lounge chair, and the lounge chair is then transformed back to the curved chair, and the curved chair is transformed back to the bed. So this is like a kind of triangular transformation. From one thing it is transformed to the second, and from the second it is transformed to the third, and from the third it is transformed back to the first object. As I mentioned, that neural network learn the structure of the objects. So if it learn the structure of the objects, it should be robust to the noise. So what we did here, these are the input samples. So what we did, we put random noise to this input image. So here we can see that we heavily corrupt this input image by putting the random noise on each object. So this is the input, this is the object, and we corrupted it here. Similarly, we corrupted this object here, this is here, and we provided this corrupted image as input to this our architecture, and check whether it can reconstruct the object back or not. So this is the final output. These are the results from each neuron actually. So but this is the result from the full layer. So here we can see that it can reconstruct this aeroplane from this noise input. Similarly, it can reconstruct this bathtub from this noise. So it's the output is somewhat clean. So it means that this neural network learn the structure of the object. So here we can see that all the with the little noise is reconstructed by using this by using the proposed feature extraction and reconstruction neural network. Here I am going to show the video of the feature interpolation using our approach. So here we are interpolating from bed to this gaming chair. Now it's slowly transforming between different objects. So here we can see that now it will transform back to the bed. So this is how our feature interpolation algorithm works. It transforms between the three different objects, like it transforms from one object to the second object, and from the second object to the third object, and from third object it comes back to its original object. Similarly, here I will show how this performs the classification. So this is the input object. I want to classify this input object, and if it is wrongly classified, then what is that wrongly classified object. So this is input to the network. Now we reconstructed this from the local layer, but when we reconstruct it from the recognition probability, it gives us the bit, and this is the corresponding bit in the input data. Similarly, this is a second example. We give it to the network, we reconstructed it from the local layer, but when we reconstruct from the recognition probability, it gives us the bed again. So this is how this wrong classification works. Like the selected clusters in the feed forward and the feedback path are different, and when they are different, when we reconstructed those features, it gives us these objects, like how it perform this wrong classification. So this was all about our research in terms of the interpretation of neural network using the visualization based approach. We adopted different training strategy to remove the redundancy of the multiple decoder. Like the previous researcher used multiple decoder to visualize different layers. Similarly, we also proposed a response field-based reconstruction algorithm, like how the neuron collaboration works. Like single neuron is meaningless. Actually, neuron works in collaboration because of the behavior of the convolution operation. So we propose a response field-based reconstruction algorithm to show how these neurons collaborate. We also showed the misclassification and feature interpolation algorithm. Uh, and we also investigated the capability of neuron, how it learned the structure of the objects. So what we did, we put noise in the input data, and then we reconstructed, baked it, whether it can reconstruct it or not. So it showed the capability of the neuron to learn the structure of the input objects. This interpretation approach has maybe extended to and it can be connected to the semantic knowledge, because we can see that our approach is able to reconstruct the parts of the objects, whereas semantic knowledge is combining the different parts and then decide the uh, and then give the result about the whole object. So this can be connected to the semantic knowledge. Similarly, this approach can also be used in the online learning by correcting the classification accuracy. So there are many directions which we can go through by using this approach. This was all about the interpretation of neural network.